Hi everyone, thanks for joining. I'm Nitish. The title of my today's talk is A New Upper Bound on Cache Hit Probability for Non-anticipative Caching Policies. This is a joint work with my collaborators from India and my advisor, Professor Don Towsley. Here is a brief outline of my today's talk. First, I'll discuss the motivation behind this work, followed by some background, and then I'll introduce our proposed hazard rate based upper bound on caching policies for object hit probability. And then I'll also discuss a few extension of our work to variable size objects and trace driven simulations, followed by some future work. So the basic objective of caching, one of the basic objective is basically to maximize the hit probability. So we have users, those request objects to first to the caches, and if the cache has those objects, then it returns it to the user and it's considered as a cache hit. If it doesn't, then it is forwarded, the request is forwarded to the origin server, and then it's considered a cache miss and the object is returned to the user from the server directly. So one of the primary goal is to maximize the object hit probability, which is nothing but the number of requests that are served from the cache divided by the total number of requests. So caching has many dimensions associated with it. For example, depending on when do you want to store the object in the cache. If you want to store before it is needed, it is known as prefetching. If you store it on request, then it is known as non-prefetching. And also, if you want to store it or not, for example, if you must store the object when it is requested, then it is known as eviction. And when you may or may not store the object, then when it is requested, then it is known as admission. And similarly, if you know the future request process and your caching decision depends on that, then it is called anticipative. And if not, then it is non-anticipative. So there are many caching policies that has already been proposed in the literature. Few are recency based, few are frequency based, but one primary question that arises here is that with so many policies, how do you evaluate the performance of these policies? One answer can be if we are able to find an upper bound on the object hit probability for all these policies, then what we can do is we can compare the upper bound with the individual object hit probabilities achieved by these policies and then can say how far are they from the upper bound. So with that in mind, many previous work in the literature have studied this problem, finding on the upper bound on object hit probability. For example, for equal size objects under independent reference model, it is optimum to basically cache the most popular content all the time. So this is also known as static caching or LFU. And another thing is when the request process is non-IRM, even when it is an arbitrary request process, Belledy's min algorithm will give you an upper bound on the object hit probability. And it's basically you evict the object whose next request is farthest in the future. And this is anticipative, that is, it needs to know the future request process, and it is non-prefetching. Similar works have been done for variable size objects, but finding optimum is NP hard in this case, but approximate solutions do exist here. And people have also considered finding an upper bound on object hit probability. In this case also, for example, foo and pfoo methods, which are anticipative, that is, they need the knowledge of the future, and they are also non-prefetching. So a natural question arises here is that would we be able to find an upper bound on object hit probability based on limited statistical knowledge of the object request pattern in an online manner, in an non-anticipative manner? And the second question is, we should have more assumptions, more general assumptions than the independent reference model in this context. So what we do here in this work is basically propose such an upper bound, which is based on the hazard rates. So our proposed upper bound is non-anticipative and prefetching based. And So this is a brief background on the hazard rate function. So what you have here is, for example, if content or the object I is requested at these time instances from t1 till tk and so on. And suppose you want to compute the hazard rate function associated with object I at time t, then what you can do is you can you have the knowledge of the history of this object requested before time t for the object I, which is not denoted here as hi of t, and you can compute basically the hazard rate function at time t for object I by taking the ratio of the conditional density function at time t for object I to that of conditional CCDF of object I at time t. So this is your hazard rate function shown here, and and then the system model that we consider here is basically we have a single cache of size B and object catalog 1 till n of size n with equal size objects. We'll discuss about the variable size objects soon. And we have very minimal assumptions on the object request process. That is, they can be dependent. And one important assumption is that the HR function, hazard rate function that we discussed just in the previous slide, should be well defined at all points of time. So with that in mind, let me describe briefly our hazard rate based upper bound. So what you can do is at any time t, you can compute these quantities, lambda I star of t, which is the hazard rate function of object I at time t. Once you have all these values from 1 to n, what you can do is you can order them in a decreasing order. So you get these values now in ordered in a decreasing fashion. And then what you can say is that if the object that is being requested belongs to the top B hazard rates, then it is a hit. Otherwise, it is a miss. So this bound, so this will give you an upper bound on all non-anticipative prefetching based or non-prefetching based caching policies, and then this upper bound is similar to instantaneous LFE or the static caching that I discussed, which is optimal under IRM, and we're able to show that HR based this ordering will give you an upper bound on all policies that are non-anticipative. So we do have some simulation results. For example, for equal size objects, we plot the object hit probability as a function of cache capacity. Colors here represent various upper bounds and realizable caching policies. We have taken the number of edges to be 1,000 and the number of requests are 500,000 generated according to generalized Pareto inter-request times. So note that here is the hazard rate bound, which is shown here in the red curve, is tighter than the Belladis bound, which is shown here in pink. And we also find similar results for many of the other inter-request time distributions. We're able to extend this bound to variable size objects in terms of the number of byte hits, not the byte hit probability, in terms of the number of byte hits. So we're able to map it to a fractional knapsack problem and compute the upper bound. Similarly, in case of the number of objects hits, we're also able to find an upper bound by mapping it to 0-1 knapsack problem. And the final order would be you just basically order them in a decreasing fashion according to this ratio, HR over size, and then just consider it as a hit if the object belongs to the top B values according to this ratio. We do have some similar results for variable size contents. Again, you have 100 objects that are being requested according to a generalized Pareto inter-request time distribution. Total number of requests 10 to the power 5 here. Again, the red curve, which is the hazard rate based curve, is indeed an upper bound on all the other policies that are non-anticipative. And similarly, we do have some very preliminary results on real world data trace. So we consider a IBM WebAccess trace here. And we plot the object hit probability as a function of cache capacity. And again, these are the properties of the trace. And what we can see here is that, again, hazard rate bound is indeed an upper bound. thing to note here is that to compute the upper bound for the real world traces, what we did was we considered a parametric fitting to the generalized Pareto distribution for the object request patterns. And we find that HR based bound is indeed an upper bound. Future directions include coming up with a realizable hazard rate based policy that considers prefetching cost. Also come up with estimators for hazard rate, which are non-parametric and in an online fashion for the request rate for the real world data traces. And we would also like to find a closed form upper bound for some spatial cases. And that's it from my side. And I'm open to question. Thank you.